Welcome to the third video in the series of Intro to Malware Reverse Engineering. We are going through the labs in the textbook Practical Malware Analysis by Michael Sikorski and Andrew Honig. We are working in a Windows XP virtual environment. This is the virtual environment, the RME Gen 2 environment, version 24.04. So if you are on that version or later, it should look a lot like this, except maybe a different wallpaper. And we'll have all of the tools and software and collections of binaries that we will be working through. We are doing Lab 5-1. We are getting into Advanced Static Analysis, and we will be using the IDA Pro freeware version. And we'll go ahead and open this up here. And this is the environment that you will look at. Now, this is a very long lab, and I'm going to be going through this fairly quickly. Hopefully I do not forget anything. I've got my notes in front of me, but we are going to be scooting because neither you nor I want this to be a 45-minute video. Starting off, jumping in, we are going to analyze the Lab 05-01 DLL. We're going to analyze it as a portable executable file, and there we are. I'm going to do a little bit of rearranging of the environment here. I'm going to go from the graph view to the text view. I just did that by hitting the spacebar. And rather than have all of these windows crowding my icebox, I'm just going to maximize them, and you can navigate through them using the tabs right here. In fact, I'm going to pause this momentarily and return after I have rearranged the toolbars up here to give me even more space. Now, this is your environment. You can do with it as you wish, but I like to have a lot of room to work around. So, jumping into the first question, what is the address of DLL main? Now, when we opened up this DLL here, it took us automatically to this DLL main subroutine, which is the entry point for the DLL, and we are at address 1000D02 E as in Echo. And if you were to scroll around and lose that point, you can go up here to jump by name, sort by name, and we will have our DLL main right there. And there are a few different ways that you can get to that. As you get used to this IDA environment, you will find your own ways through it. There are multiple ways to do pretty much everything. I'll touch on a couple of them, but the rest of them are up to you. So that 1000D02E, that is the address of our DLL main entry point. You can see also that it is cross-referenced to DLL entry point. That is not part of the actual binary that is put in there by the compiler, so it is not technically the code that we will be looking at. We can ignore this DLL entry point. Moving on to number 2, use the imports window to browse to get host by name. Where is the import located? So the imports tab will take us to the imports window. We can sort by name. And look at that, it put us right in the G's. But what do we not see? We do not see get host by name. That is because this is not a case-insensitive sort. You'll notice that all of these are capital letters. We will need to scroll down to the second set of G's. And here it is. We have get host by name. We can find the address in the address column, or we can double-click it, and it will take us to get host by name in the iData section, and we can find our address there. Moving on to question 3. How many functions call get host by name? We already have get host by name highlighted, so we can right-click on this and jump to cross-reference to operand. That'll bring up this window here, and we can see that we have line 1 of 9. Depending on the version of IDA Pro that you are using, it may have line 1 of 18. You can see this type column here. We have all R's, but Some versions of IDA Pro will count references twice. You will have an R type, which is read, and a P type, which I believe is pointer. You can kind of ignore the double ups and, in fact, sort by address, and that will kind of get you sort of coordinated and grouped up here. Speaking of grouping up, we do not have 9 functions that call getHost by name. We actually have 5. If you look at the address here, you can see 1074 is in there 3 times, 1365 is in there 3 times, and then we have 1, 2, 3 other functions. So 2 plus 3 is 5, and we have 5 functions that call getHost by name. Question number 4, focusing on the call getHost by name located at the address 100011757. Now to do that, we can, let's see here, go to jump to address, or we can also hit the G key on our keyboard, a nice little shortcut, and we will enter 100011757, and it takes us to this call getHost by name. Can you figure out which DNS request will be made? This is where we are getting into the reverse engineering part of it. We see the getHost by name. Now, this is all called from top to bottom. We can follow this in order by moving up or down this list here. So we see call getHost by name. So getHost by name takes one parameter, and that parameter is name. It is going to pull that parameter from the heap. So getHost by name only has one parameter. It's going to pull that parameter off of the top of the stack. And where does that data in the stack come from? Well, in this case, it is pushed from the EAX register. Whatever's in the EAX register will be pushed onto the stack and then get given to the getHost by name as a parameter. Where does that come from? Let's move up the stack, up the function here, and we can see that whatever is in the EAX register, we are adding D positions to it. So if we had a string, we're going to move in 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D positions and start reading from there. Where does that come from? We can see that move, we have a move here, and we are moving from the offset 10019040 into the EAX register. We can double click on that and find that offset. That offset is a string right here. This is RDO, in brackets, pics.malwareanalysis.com. And we know that we are moving D characters in, so 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, and that puts us on the pics.malwareanalysis.com. That is the string, that is the DNS entry that we are going to be querying to get our IP address. And we can actually follow it further by following this offset that IDA has very helpfully named for us based on the string. And we can go all the way to where that is in the .data section. And we can see that full string right there. So that is the answer to number 4, pics.practicalmalwareanalysis.com. And of course, like a browser, we have the forward and backward buttons here, so we can go through, back to that, and back to where we were working. Question number 5. How many local variables has IDA Pro recognized for the subroutine at 1001656? We're going to use that G shortcut to go to 1001656. So here we are. Scroll up, and this is the entry point to our subroutine 1001656. And below it, we have all of the local variables and parameters. They are all lumped into one. And we can tell local variables because they have a negative offset. So you have the type, and then you have the offset. This offset is negative 675, 674, 670, moving on down, and we have a positive value here, so we do not count that as a local variable. Now, if you were to count these, you would see 20 local variables. There are more than 20 variables in this function. However, the IDA Pro 5.0 freeware version that we are using is limited to 20 20 local variables. So anything beyond that, it is not going to show us. Unfortunately, it will also not tell us that it is not showing us the full number of variables. If you look at the textbook, I believe the answer is 24 local variables in total, but we can see only 20. Now, why do we ignore this positive right here? Positive offset. Well, that is for question 6. How many parameters has IDA Pro recognized for the subroutine at this address? And that is 1. We only have one positive offset, so that is 1 parameter. And we see it as argument 0. Why this says parameter up here? Yeah, I'm not really sure. Listen, I'm learning this just like you are. Moving on to question number 7. Use the strings window to locate the string \cmd.exe/C in the disassembly. Where is it located? Let's move over to our strings tab here. I'm going to sort by string. I can also, in fact, let's do a search. We're going to search. It is \cmd.exe. And it took us right to it. Fantastic. Expand the address column so we can see the full address. And it is at 10095B as in Bravo 34. And we can double click it and it'll take us right there. Now, this is not actually the area of code that we are interested in seeing. That's referenced in question number 8. This is simply where the strings are stored in this DLL. But since we are here, let's take a look around and see if we can intuit any kind of information from what we see in the strings in this area. So we have our cmd.exe. We also have a command.exe. We know that it's going to be launching a command shell. Now, hi, master. I don't expect to see that in many binaries, in many legitimate programs. Welcome back with really weird capitalization. Are you enjoying today? Okay, so right off the hop, this looks not legitimate. You have machine uptime, machine idle time, encrypt magic number for this remote shell session. Well, that just gave up the whole deal right there. This is a remote shell application. This is something that we learned about in, I believe, chapter 4, and we are seeing it in the wild here in this code analysis. But now that we've had our little tangent, let's go back to question 8. What is happening in the area of code that references cmd.exe? So let's go back and we can go to this data cross-reference, this subroutine right here, double click that. Now we are in the code section that we need to be looking at. And in this case, I'm going to hit spacebar again and go back into the graphical view. And this is going to let us look at the code flow and see a little bit better what's happening, rather than having it in all one big boilerplate, non-divided mass of text right here. Let's go up the graph. So up a little higher in the graph, we see our hi master. This is likely what the attacker is going to see when they log into the system, when they open a shell to this remote shell. And let's go back down the stack. We can see we've got a decision here. One points to cmd.exe, which is the newer version of the command prompt, and command.exe spelled out. That is the older version. And definitely what we are going to see in here is it's going to check what version of Windows are we on. So whatever version of Windows, if it's older than probably Windows 2000, it will launch command.exe. If it is Windows 2000 or newer, cmd.exe. And then, of course, we go down down the function a little ways, and we start looking at, there we are. We have strings that look like commands. We have quit, exit, cd, which is change directory, nmagic, idle, uptime, language. These are all switches to capture commands that are given to it and then execute a function based on what that command is given. So that is the rough answer to number 8. We're just looking around and seeing, okay, what is this actually doing? Question number 9. In the same area at address 100.101C8, it looks like dword 1008E5C4 is a global variable that helps decide which path to take. How does the malware set dword address given? For that, let's switch back into the code view. Again, that is the spacebar keyboard shortcut. And we're going to go to that address. I use G, as in go to. And we are looking for address 100.101C8. Okay, so we have our dword. We are at the address given to us in the question, and we see that it is being compared to whatever is in register EBX. But what is in dword? For that, we can go into jump to cross-reference, and we see 3 cross-references. We have a compare, another compare, and a move. Move is going to be where this dword is set. So our next jump is to there, and right above it we have a subroutine, 3695. Double-click that, and we are in that subroutine. So right off the bat, at the top of this subroutine, we have version information equals OS version info, pointer. Yeah, this is going to be looking at what version of operating system, what version of Windows is it running. And we are calling this get version exa. This get version exa is going to return the information that is wanted by this function. We're going to do a string compare, a set, and then we're going to return the information. So this subroutine is getting the version of Windows that this program is running on, and that is going to be, and I'm going to go back, what is set into that dword. So it calls this subroutine, which sets the value in EAX, register EAX, and then it's moved from EAX into that dword. Question number 10, we are halfway there. A few hundred lines into the subroutine 1000FF58, a series of comparisons use memcomp to compare strings. What happens if the string comparison to robot work is successful? Once again, we're going to use that G shortcut key and hop to the address that we are given, 1000. That's a lot of zeros. 1000 FF58. So here we are at that instance of robot work. And if we scroll around, we see idle, uptime, language. We've been in this section before. This is the section where all of the commands that could be given to this remote shell are stored and decisions are made. In fact, if I spacebar it, yes, this is exactly where we were when we made that discovery. Now, so it's going to take that robot work string, and we're going to do a memory compare to what command it has been given. And if it was given the robot work command, we are going to launch this subroutine right here. Here we are at that subroutine, and you can see as we scroll down, all right, we can see that it's going to call this reg open key. If we hover over it, we see the parameters that it takes, and above it, all of the values that are pushed into the stack that will be used as those parameters. It's going to open the software Microsoft Windows current version, and this hex value right here, that is the registry hive that it will be opening. If you look up the values for this reg open key, you can see that 8, lots of zeros, 2H refers to HKey local machine. Once we have opened this registry hive and we've gone to this registry key, we're going to come down, execute more code, and that's when we come to the reg query value. So we're opening the registry key and querying the value of the key named work time. This is likely the work time, the time of day that has been assigned to the malware to do its job, or perhaps when the actual computer is most often used. We don't know, we can just kind of guess from the name, but we're going to query that value, we're going to get it, and then we're going to output this string, robot_worktime, and the formatted value. Further down the line, we'll go work times, plural, access that registry key, and do the same thing. So the robot work time command just accesses these registry keys and exports those values over the console shell. Moving on to question 11, what does the export PS list do? First thing that we need to do is find the export PS list, and we can do that under the Exports tab. PS list is right here front and center. Double-click that, which takes us to the subroutine. After that, it's just a matter of walking through the calls here, looking for anything interesting. Right off the top, we see a subroutine. Double-click that, and we're looking at get version exa. IDA helpfully tells us that this gets extended information about the version of the operating system, and we are doing string compares to version information.dw platform ID and DW major version. So we're definitely getting the version of Windows, and we return from that function and proceed through. We jump to this location where nothing interesting happens, and we go back. Look for our next jump. We're jumping, if not 0, to this location where we are jumping in, where we are calling a subroutine. That takes us to this subroutine here. It's a little bit of a longer one, so we can just scroll through and see if anything jumps out at us, like perhaps this create toolhelp 32 snapshot. Now, if we go and take a look at this, it's a very interesting API, and what you can do with it is enumerate the processes that are running on the system. You can get threads, you can get modules, you can get heaps. Lots of information about what's actually going on with the system here, and return that to the functions. Let's look at, we go to this jump to location here, and we see process ID, process name. So we are definitely sending a list of running processes on the system back to that attacker. And that appears to be a good idea of what that subroutine is all about. Question 12. Use the graph mode to graph the cross-references from sub_100004E79. Which API functions could be called by entering this function? So first thing we want to do is go over to the Functions tab. We have sorted our functions by name and found our 100004E79. We can double-click that, which takes us directly to the subroutine. For the graphing function, we right-click the subname, chart of xrefs from, and we can see the APIs that are called from this function. They are in purple here. There are a few different ones to choose from, but the one that pops out at us is get system default lang ID. So the next part of the question, based on the API functions alone, what could you rename this function? More than likely, it gets the language ID, so we can right-click and rename, and just call it get language ID. Now, this will populate throughout the rest of the IDA, and wherever there is a reference to this function, instead of getting a sub_numerical name, we'll go ahead and get that get language ID. Question 13. How many Windows API functions does DLL main call directly? So let's go on back to that DLL main. And we just went to that through the Functions tab. And we'll use a very similar graphing function. Now, in the book, it says to use the chart of xrefs from. it took me a long time to figure out how to get the answer that they had. So what you want to do is come up here to View, Graphs, User XREFs Chart. This gives you the options that are shown in the book, and we want to not include cross-references too. The rest of the options are okay. Let's do a recursion depth of 1. And now that is a lot cleaner than what we would have gotten otherwise. So we can see that the Windows APIs that it calls are 1, 2, 3, 4. These 4 right here in purple. And the next part of the question is, what about at a recursion depth of 2? So we will go up to View, Graphs, XREFs Chart. Change that to 2. Now remember, every time you come into this User XREFs Chart, it resets the options to default. So whatever you've set, it does not carry forward to the next times that you are using it. And at a recursion depth of 2, that is a lot more to sort through. What you can do is go through and just scroll and count. I will leave the counting up to you, but quite a few more in this one. And question number 14. At 100001358, there is a call to sleep, which is an API function that takes one parameter containing the number of milliseconds to sleep. Looking backwards through the code, how long will the program sleep if this code executes? So first thing that we need to do is we need to jump to that address, and we will use our G key and 100001358 takes us right to that sleep function. We know that it takes one parameter, which is the number of milliseconds to sleep, and that parameter is going to come from the stack, which means that we need to push a value into the stack. In this case, it comes from the EAX register. The last operation that we see on the EAX register is a multiply, imul, integer multiply or unsigned multiply, and we are multiplying the EAX value by this 3E8 hex value. IDA Pro lets us switch that to a decimal value. We can see that it's 1000. So whatever was in that EAX register was a value of seconds. We are multiplying it by 1000 to get milliseconds, and that's what we feed into this sleep function. Right above that, we see A to I, which is a string to integer function, and we know that below this line, we're dealing with a number. Above this line, we're dealing with a string. The A to I function, of course, is going to pull from the stack. So we have to push the value from EAX. So we have a string value in EAX that is pushed to the stack into the A to I function, which gives us our number. We have an add EAX, and we have that D value. Let's go ahead and switch that over to decimal as well. So we pulled a string value from, and this is the move, we are moving from this offset into EAX a string value, and then shifting over 13 characters, pushing it into the stack, converting it from a string to a decimal, multiplying it by 1000, pushing it into the stack, and sending it to the sleep function. So now we just need to find this offset. We can double click that, and here we are in the offset. I believe that this is an error. So if you look at this 19020 offset, there's not a string over here. However, if you go to 19024, there is. And you get this is NTI 30. And if we count, that's 13 characters, and we get our 30. So for the purposes of answering the lab, I'm going to go with this 19024 offset for this string. And of course, the book, matches the book answer. But I was very, very confused here, and I'm just going to chalk it up to there's a mistake. But We have 30. We know that we have that string brought in here, shifted over 13. So we have a string value of 30, which is converted to an integer value of 30, multiplied by 1000, fed into the sleep function, and we get our sleep of 30 seconds. Question number 15. At 1001701, there is a call to a socket. What are the 3 parameters? Again, we'll need to jump to that address using our G key. 1001701. And here's our call to the socket. We know that parameters are pushed to the stack first, and then fed to the function. And we know that the stack works like a stack. The last value in is the first value out. So we see our 3 parameters are AF, type, and protocol. And we will work up. So AF of 2, type of 1, and protocol 6. If you look at the WinSock2 documentation, it will give you the values, the parameters, that match these integers here. So the first parameter that the socket function needs is AF, and that refers to address family. If you look at the documentation, you'll find that an integer value of 2 refers to Internet Protocol version 4, so IPv4. Next is the type, and the integer version of 1 refers to the socket stream, a socket type that provides sequenced, reliable, two-way connection-based byte streams with an out-of-band data transmission mechanism. And last is the protocol. And for the protocol, the integer version 6 refers to TCP, or Transmission Control Protocol. Moving on to question 16, using the MSDN page for socket and the named symbolic constants functionality in IDA Pro, can you make parameters more meaningful? What are the parameters after you apply changes? Yes, as a matter of fact, we can. So if you right-click and use standard symbolic content, it will give you a ton of symbols here. So you will have to search, and looking at the documentation, you can tell that it's AF INET. We'll double-click that, and it makes the change. We will do the same thing with the other 2 parameters. Now that we have used our symbolic constants, instead of having integers here that mean very little to us, we have actual named constants. Question 17. Search for usage of the in instruction, which is opcode ED. This instruction is used with a magic string VMXH to perform VMware detection. Is that in use in this malware? Using the cross-references to the function that executes the in instruction, is there further evidence of VMware detection? So what we will do is we will use the search, come down to sequence of bytes, and we are going to search for ED. I'm going to check find all occurrences, and that will give us the full list of all of the hex values of ED that are used. Now remember, we are looking for a particular instruction, and that is in. And if we scroll through, we only see one instance of that, and it is right here. We can double-click that and find that instance. What we don't see is any instance of VMH. But we do have hex values here, and we know that IDA will let us convert between different byte styles. And if we convert it to text, we can see that we have the VMXH here. And down here as well. So now that we've discovered that, we can go up to the top of the function here and Jump to cross-reference. We have 3 addresses. They all say install, so they are all probably very similar. And we pick one. And this is the call to that function that looks for that vmxh. If we look just a little bit further down, we can see found virtual machine install cancel. I suspect if we jump to another cross-reference, found virtual machine install cancel. So yes, in this malware, it does look for virtual machine signatures, and it will abort installation of whatever this is if it finds it. Question number 18. Jump your cursor to 1001 D988. What do you find? Once again, we use our hotkey to jump to 1001 D988. And what do we find? We find a bunch of individual lines of seemingly random ASCII text. And that's all the question asks us. Until we move on to number 19, if you have the IDA Python plugin installed, included with the commercial version of IDA Pro, run lab5-1.py. That's an IDA Pro Python script provided with the malware for this book. What happens after you run the script? Now, the freeware version that we have does not have that functionality. What we can do, however, is open Notepad, open that Python file, and take a peek and see what it does. This is a very simple script, and if you have any coding experience or scripting experience at all, you can kind of muddle through it and see what it does. The SEA equals screen EA, that is more than likely something specific to IDA, but you have a for loop in range from 0 to 50 bytes. You increment through the bytes. The decoded byte is B exclusively ORed. That's not an exponent, that's an exclusive OR operator, with the hex byte 55, and then patch byte, SEA plus 1 decoded byte. That is probably just passing it back to the IDA. What this is doing is it is decoding this string. Now, when you have a string in IDA Pro, and I'm just going completely off script here because this is for question 20, if you have a bunch of individual characters, you can right-click or use the A hotkey to build a string, and it takes all those individual characters and lumps them together. The other thing that you can do is highlight, copy the string, and take it out of the virtual environment to any of the websites that will let you XOR a string with a byte file, and you can actually decode that, and it gives you the string in the book, and it's something like, "This is malware, haha, how are you?" Something like that. But what it does do is it gives you an introduction of using Python scripts to extend the functionality of IDA Pro to work with stuff that you have here in the editor. So going back to the lab questions, the last few. 19 you are unable to do with the freeware version, but you can use the, your eyeballs to look at the script and see what it does. Question 20 asks you, with the cursor in the same location, how do you turn this data into a single ASCII string? We saw that with the right click and the keyboard A shortcut, or I call it stringify. And then question 21, open the script with a text editor. How does it work? We went over that at the beginning of it. It just XORs the individual characters with the hex value 55, and it decodes it to a readable string. So there you have it. That is Lab 5.1 from the textbook. Hopefully this was helpful. I think we made it under the 45-minute mark just barely. I've been enjoying doing this. I apologize the video came out late for those of you who are following along in real time. It just happens to be allergy season in Florida, and I just got my voice back. So good luck to you all, and I will see you on the next one.